All right. Well, thank you, everybody, especially in United States, and people wake up early to attend this webinar. I'm very glad to have two researchers that I feel really fortunate to get to know better during this webinar. Their paper on why a vehicle stop uh, is really an example of research we published in IJGIS recently showcase how we should use machine learning to analyze geospatial data. And we have a lot of a research paper we recently published in IJGIS applying machine learning, deep learning on various geospatial data. But the editors we discussed, and we find that this is the paper seems to be most systematically give the logic and reason why we need to use machine learning and how to use it in the right way. So I'm very happy that Dr. Carl Reuer, I'm sorry, I cannot pronounce your last name very well, and
No
Dr.
problem.
Stan from Grenzinger are willing to take the time and then give us a presentation and more insight on their thinking and maybe a broader perspective of the using machine learning on trajectory data. We will have their presentations for 30-35 minutes, and then we will open the floor for discussion. I hope you will prepare some questions and during their presentation. And we also make their paper, IJGIS paper, openly available. You can free download the paper from IJGIS website free. So after the presentation, and I hope that you will also go back to check out their really very well written paper and then to see that how you might looking at your own research in a different way and maybe contact the author for potential collaboration. So without further ado, Carl, let's get started.
Yes, thank you very much, Mai, for this kind introduction. So I'm just sharing my screen, the presentation. I hope you see it. Okay, so I'm going into the presentation mode. So thank you for inviting us to have the opportunity to present our paper, Why Did a Vehicle Stop? A Methodology for Detection and Classification of Stops in Vehicle Trajectory within this series of IJGIS webinars. My name is Karl Rehl, and I do the presentation today with my colleague Stefan Granzinger. Also, Simon Greuchenik, a colleague of us, was a co-worker, but he is not presenting today, but he also contributed to the paper. So just to briefly introduce ourselves and to give you a short outline what we will talk about. So first we say who we are and what we do. Then I give a short introduction on vehicle trajectories. If you're not so familiar with the concept of trajectories, so I will briefly introduce it. Then I will talk about the stops in vehicle trajectories and what they are and how can they be detected. And then I hand over to my colleague, Stefan Granzinger, and he will talk about the machine learning part. To say the classification in two different stop categories, namely traffic relevant and non-traffic relevant. And at the end, we will conclude and give some outlook on future work. And then we are, of course, open for the discussion and looking forward to answer your question and to get into a discussion. So just at the beginning, my colleague Stefan Granzinger he has a master in business administration, economics, as well as social economy and a PhD in economics. And myself, my background is computer science. So I have a diploma degree in computer science and a PhD in geoinformation. And so we work together at Salzburg Research, which is a non-university research organization based in Salzburg. And our main topic of this organization is to work in the area of motion data intelligence, how we call it. So getting out value from motion data in 5 different research groups, and we both are from the mobility and transport analytics group, which basically means that our main research topic is to deal and to analyze motion data. And our focus, as is what is also the background of the work, is that we are dealing a lot with vehicle trajectories. So this is our main data category for our work. And we are collecting this data from different vehicle fleets with contracts. And we are collecting this in a real-time manner. So we also have systems running in real time, also processing this data in real time and generating traffic information out of this. But on the other hand, we have a larger, huge corpus of stored vehicle trajectory, around 100 million, and they are growing every day. And this equals to 30 billions of position measurements. And you see on the map here the data of one day, for instance. It's mainly in Austria, but also in parts of Germany where we get this data. And with this corpus of data, we are developing our methods. And this is also one of the background for the paper, what is useful to understand. So always when we are looking at this methods, what we are developing, it's not only the question that it basically works, but we always have to look that it can work, such a method can work in a very performant way, being applied to this huge and massive amount of data. And that is also always one of the aspects. And I want to focus during the presentation also on this aspect, because that's relevant to understand why we have chosen this, especially this methods we applied here, and also for certain parameter tunings and so on, this is relevant. We are also developing our own systems, so software processing platform. Of course, we are using open source software, but also we are developing the software. We also have an own open source framework, which is called Graphium, for storing transport graphs, and which also you can access on GitHub, and which plays also a major role in this whole processing, because this this software contains the map matching module, which is a very important aspect. So just to start and give you the overall introduction. So on the one hand, what are vehicle trajectories? And we always find a very good introduction on this topic, and also a kind of reference model is coming from Kilsilevich and co-workers in the Data Mining and Knowledge Discovery Handbook. You find the reference here, and which basically says, well, if you're working with spatial temporal data, then it's always, on the one hand, you have to have a look at the categorization. Do we have a fixed location, so have a fixed sensor, for instance, or is the location dynamic? So that's the spatial category. And on the other hand, you have to have a look at the temporal dimension and say, how often basically do I measure these values? Is it a single snapshot? Is it an updated snapshot? Or is it the time series? And the third category would be to say which kind of spatial conceptualization do we have? Is it the point conceptualization, line, or area? And with these 3 dimensions, then you can classify your data. And this is what we are doing, is called trajectories. So basically, we are using point-based conceptualizations of space. As you see here on the right side, you see an example trajectory coming from vehicle. So you have this location as point, modeled as points in R2, for instance. And but it's regularly updated. So it is a dynamic location. You see the location is changing. And on the other hand, it is a time series data, because it's regularly updated and changing. And also, this is the trajectory is the concept what Giannotti and co-workers call, for instance, temporally annotated sequences of position measurements in 2D or R3. So that is basically the data we are working with, and which is also the data which is the foundation for this stop detection. So what I already showed, but to give you another impression of this 1 day data set, for instance, what we collected now in March, on 1 day, 35 million locations, 2.2 million kilometers on the road network, 40,000 hours. So quite a massive trajectory data set where we are applying these algorithms, also the stop detection algorithm. And so we always have to keep in mind whether such an algorithm is able to work on such a massive data set, and also that it could work in real time. So just also to give you another introduction or background, so typically how we are processing these vehicle trajectories. So this is in data mining, typically it's this called then the segmentation, for instance, of such trajectories. But first, before we are able to do the segmentation and analysis of the data, so the mining part, of course, you have to do a lot of pre-processing. So if you're collecting this data from different interfaces, you have to harmonize the data, you have to validate, clean the data, anonymize. So a lot of processes going on there. But today in this talk, we focus on the mining part and there on the stop detection, which is one of the mining steps and of the mining algorithms. The others are map matching on a road network, travel time calculation. It's also extracting some patterns, motion patterns. This is also in the term of data mining. This is also a segmentation of this time series or of this trajectory. And so today the focus is on this stop detection. So this means basically, are there stops in such a trajectory? Where are they? How long are they? So which characteristics do they have? This is the first question, to extract this from the trajectory. And the second question then is to classify it. So also to give you the background, so why is this relevant for us? And if you're dealing with vehicle trajectory and traffic information, so basically the use case is to derive traffic information out of this trajectory data. So as you see here on some of the pictures, so basically everybody of you knows these traffic maps where it is drawn then in green, yellow, red, and other colors. So how well is the traffic flow on a certain road segment? And the question is, so for instance, from which data sources you can derive this information, and vehicle data is one of the data sources which can be used for deriving this information. But before you can use this, you have to look at the data and at the stops, whether there are traffic relevant or not traffic relevant. So you might imagine that a lot of stops are occurring. Vehicles are driving, but sometimes they are stopping. But it's relevant whether they are stopping because they are forced by the traffic. So because they are, for instance, within a traffic jam and have to stop the vehicle, or there are even a lot more other stops where, for instance, the vehicle stops because another person is coming in or getting out, or the vehicle has to stop because of a stopover or things like this, or a U-turn, or being at the rest area, as you see, and so on. So there are many reasons why the vehicle can stop, but that is not traffic relevant, because of course all other vehicles have not to stop because of this stop. But if this is a traffic jam, or if it is at the toll gate to stop or something like this, then this is relevant and this has to be considered. So the question for us is, on the one hand, to detect the stoppers reliably, but on the other hand, then to classify it. And this is then the part what we are doing with where we are applying machine learning. So basically, the work now is divided into 3 steps. The first step is the stop detection, so to detect the stops. The second step then is to extract the stop characteristics. So which characteristics can we define? And this is the pre-step then for the classification, because the classification can only be as good as the characteristics are able to discriminate the 2 different stop classes. And so that's the overall approach. And now I focus a little bit more on the first part, namely the stop detection. And this is where we say, well, we need an algorithm which is capable of doing this detection. And so this is not a new algorithm what we applied there, but we took one from Ye and co-workers from 2009. Why we took this algorithm? So this was also one of the critics coming from the reviewers, saying, why did you take such an old algorithm? So the answer to this basically is we need an algorithm with very good characteristics, and these are we get this data in variable sampling rates, so we cannot be for sure that every point, for instance, every location is coming at the same time interval. So the algorithm has to be capable of dealing with this. On the other hand, we do not want to remove the GNSS noise. Of course, there are a lot of algorithms for doing this, but in the processing, the real-time processing, this is another step, removing the noise. And as I said before, we have to deal with massive data, and also we have to look at the runtime performance. And this is the third point for the algorithm. It has a rather good runtime performance. So maybe it does not in every case leading to the best results. So there may be better algorithms, but on the other hand, given all the different requirements, what we need with an algorithm, this was the best deal, basically. And this is also one of the very important things what we want to mention today, is that in some cases, given your special use case, it could be, or you always have to select what is the best algorithm for this, especially for this case, and dealing with or fulfilling all the requirements. On the other hand, so because this algorithm is not directly for vehicle trajectories, but it's a very common algorithm for doing a spatio-temporal clustering. It could be applied to stop points, but it could be applied to any other spatial temporal clustering. We had to do some algorithmic adaptation in order to get good results for vehicle trajectories. And this is especially has to do, and you see it on the right, two examples during this clustering process where the stop point then is located, because this is one of the main attributes and characteristics which we are working then in the classification part. And as you see, if you're doing this kind of spatial weighted, and this is the original algorithm, it uses a spatial weighting for the stop location, and you see it's quite it's not on the track itself and not on the road, but it's far away. And so we introduced the time weighting, so not only the spatial weighting, but the time weighting. And then we could move the point directly onto the trajectory, which is much more beneficial in this case for then using this stop point as one of the characteristics for classification. On the other hand, we are doing the same, that we are moving this stop point to one of the track points, what you see here, based on the half duration of the whole stop, because as you see, given the different parameters, there could be the stop point away from this track and also from the road network. And the third step is we are doing a kind of pruning, because also there could be stop points within this spatial temporal clustering, which are not at a low speed, but they are classified as being part of this stop. And also we are pruning the stop points so that they are below a speed of 10 kilometers per hour. So this were the adaptation, and they're also described in the paper. And with this algorithm and the adaptation, we are now going into this day's data set of 1 day. In this case, this was from 2017. It was 50,498 trajectories. And so on the one hand, the algorithm takes two different parameters. So the first is the distance, what you are putting in this parameter, and the second is the duration. And this is also something which sounds very easy, but it's very hard to find out what are good distances and duration parameters. And so here we applied a kind of empirical tuning of these parameters. And you see on the curves on the left side, you see on the one hand, the different curves are different distances. And on the axis, you see horizontally, you see the different durations. And you see, of course, if you're not selecting carefully these parameters, you get a lot of stops in this data sets. For instance, 140,000. So the values are in thousands. So a lot of stops. Even if you're then using other parameters, you see that you could decrease the stop significantly. But on the other hand, it's always a deal not to miss any stop, but also not to get too many stops. Yeah? And so we found it out empirically that 200 meters distance for such a stop, for a vehicle stop, and 120 seconds duration at the minimum, that this is a rather good parameter set in order to get then, it's even a large sample there. You have to say this is on a daily basis data from Austria, and even nearly 6,000 stops are a lot to get classified. And in order to work then towards this classification part in the machine learning, we selected 2,032 stops of these detected stops and manually classified them. So we looked at every stop and looked at the trajectory and made sense out of it. Rather, is this a non-relevant stop, which we now here drawing in blue, or is it a travel relevant? And what you already see here, that they are not equally distributed. There are much more or many more traffic relevant stops compared non-traffic relevant compared to the traffic relevant. And this will be one of the things that then also Stefan will focus on, what this means for the machine learning part, because that's the relevant finding if they are not equally distributed. So I'm coming to my last slide now, and this is the second step, the characteristics for classification. And there are also very important design considerations why we did it in this way. So on the one hand, we tried to came up with characteristic attributes that are rather discriminating for the two classes. And that's not an easy thing. We tried a lot with different also parameters and attributes. You see stop duration, distance, average speed, minimum speed. And also we have some other attributes we are using. So how far, what is the spatial location of the stop? So how far is it from a road away? And from a high level road for other roads and so on. So these are our main attributes. Of course, now you can say, well, you could use also another data set like a point of interest data set, and then maybe this classification task would be easier. It could be. So this is one of our future questions. So what we could try out. On the other hand, we decided to go only for two different data sets, the trajectories itself and the road network, and no other data sets, because that is something what you can get easily, and what you have. You have to imagine that also if with any other data set what you're using, you have to get this data set and you have to ensure the quality of this data set because otherwise you also will have misclassification. So this is a very important aspect, and we are also happy then to discuss this, what it could maybe have which benefits to using another data set or to do it only with this data set. But of course, as you see from some of these attributes, it's only with these 14 attributes we are using. It's hard sometimes to classify exactly if it is the traffic relevant or non-traffic relevant stop. But this now is the part for Stefan, and I hand over to Stefan to give you the insights on the machine learning part.
Okay, thank you, Carl. I hope you can see my screen.
Yeah, Stefan, we can see your screen. Yes, now in the presentation mode. Thank you.
Okay, thank you. Thank you for this information. Now I will present you the machine learning based stop classification approach, which we applied in our paper. And just a small outline, what I will talk about is the selection of the machine learning algorithms, the attribute selection, the pre-processing of stop characteristics. Then I will talk about the algorithm training and the parameter tuning. And last but not least, I will tell you about the performance measures before I present you the results of the paper. Okay, let's jump into the first point in the selection of the machine learning algorithms. So we evaluated 6 different machine learning algorithms, including 4 tree-based methods. The first is the bootstrapping aggregation method introduced by Breiman in 1996, and the random forests. So the random forests just includes random feature selection in the bagging process. And next to these 2 methods, we also apply some boosting algorithms. So adaptive boosting introduced by Freund and Shapir, and extreme gradient boosting introduced by Chen and Gostra. And yeah, boosting is quite interesting because it puts more weight on misclassified observations, and therefore we think this maybe could improve the performance measures. Okay, then we also decided to evaluate the k-nearest neighbors approach. This is a quite intuitive and easy to understandable machine learning algorithm, and it's quite intuitive. Moreover, we evaluated an artificial neural network and an ANN, and it's necessary to say that we applied a single hidden layer ANN. We also applied some more sophisticated and more complex ANNs, but they didn't show much improvement in the performance or any improvement in the performance. And so we decided to stay with the simple ANN. Okay, so you know which machine learning algorithms we applied, and now we move on to the attribute selection, because we have to answer the question which attributes we choose for our final models. And as Carl has explained before, we extracted 14 different features or attributes which could be implied in our model. And to select the most important ones, we adopt a method introduced by Diaz-Boriate and De André, and it's a random forest. We apply a random forest and use aggressive feature selection. So in each round, we eliminate the 20% of the least important features, and the minimization criterion is the out of bag error. We can see the results on the top right figure, and we see very interesting, with already 2 variables, we have a quite reasonable and good model with an out of bag error of around 19%. With only distance to the next high level road and average speed, we get quite good results. And with using 3 variable attributes, the out of bag error starts to converge around 15%. And with 11 variables, we get the best results for the final model, and with an OBB error of around 13%. However, on the right bottom figure, we see the most important variables. Here we use the mean decrease in accuracy, which means if you randomly permute these respective attributes on the y-axis, we have a loss in accuracy of the number which is on the x-axis. So if we randomly permute distance to next high-level road among the observations of our sample, then we would have a decrease in accuracy of around 5.3%. So this means this variable importance figure. And so these are the most important attributes we use, and we decided to use these 11 variables for our final model. Okay, let's move on to the pre-processing of our stop characteristics. Here we decided to normalize our attribute values with a min-max normalization. Normally, it's not mandatory for all machine learning algorithms we use in the paper. However, for some, it's mandatory. For example, for the KNN, it's mandatory, and therefore we decided to have a uniform data set to normalize the attribute values for all machine learning algorithms. Of course, it's necessary to randomly split our data into a training and a test data set. So we decided to take 75% for our training data set, which we use to train our model for the hyperparameter tuning and so on. And with this training, we get our final model, which we apply to the test data. And this is where we get our performance measures from. And interesting for you, you have seen we have acquired imbalanced data set. So 80% of our stops are non-traffic relevant, but 20% are traffic relevant. So in the literature, it says, yeah, it could be a problem, and normally the minority class should be at approximately 50 to 90% after data balancing. But yeah, we have read some more information about that, so we decided to evaluate which data balance method leads to the best results in our case. So we run a random forest for the imbalanced data set, one for which we applied oversampling. Oversampling means just that we replicate some observations of the minority class, but this could lead to some overfitting. Then we use undersampling, which means that you simply eliminate some observations of the majority class. In this case, we lose some valuable information because we lose some observations of our sample. And then also, interestingly, the literature says, yeah, SMOTE, maybe SMOTE means synthetic minority oversampling technique introduced by Travel and co-workers in 2002. This could also lead to good results. Just in case you don't know what SMOTE is, you take, for example, a k-nearest neighbor approach. You take a minority class, and then you take k-nearest neighbors, for example, 30 k-nearest neighbors. And then you take the feature vectors of the minority class and the k-nearest neighbors, and then you take the difference between these two feature vectors. And then you multiply this feature vector by value between 0 and 1 that's randomly chosen. And then you have new observations produced out of the minority class. So therefore it's called synthetic minority oversampling technique. And we added the undersampling approach to this methodology because the literature says that this is a good way to handle with an imbalanced data set. So just very quick, if you need more details, maybe you can take a look to the paper. If we take a look at accuracy, ROC, Cohen's kappa, and method correlation coefficient, we see that oversampling leads to the most balanced results. So we decided to apply oversampling to overcome the unbalanced data problem in our data set. We did this for all machine learning approaches, except for the k-nearest neighbors, because here we see a significantly decreasing performance when using oversampling. So we're using oversampling for all machine learning approaches except for the k-nearest neighbor approach, so to be transparent. Okay, then let's talk about the algorithm training and parameter tuning. So what we do is we use the training data set, the 75% of the sample data, and run a 10-fold cross-validation. And we also try 10 different values for each algorithm parameter we could change for the model. And we calculate the area under receiving operator curve. Because you get the area under receiving operator curve just plots the true positives against the false positives. And for each run of the cross-validation, we get 1 point of this ROC. And if we have 10, then we can draw a line, and then we can calculate the area under the receiving operator curve. And then we get, in the case of a random forest, because here we try parameters for the features randomly selected at each step. Then we have 10 different values, and then we choose the model with the highest ROC. And this final model is applied to our test dataset. Okay. Now let's come to the performance measures. And here we have chosen 10 different performance measures. And we divide this into two families. First, the performance of the classification model. And here we have the performance of classifying traffic relevant stops. Here we use specificity and negative predicted values. And the performance of classifying non-traffic relevant stops. Here we have the performance measures of sensitivity and precision. Moreover, we have markedness, which shows us how much confidence we can have in the results, and informedness, how much information we get from our model. Then we have accuracy, the area and the receiving operator curve. Cohen's kappa is more or less accuracy when we exclude the random accuracy of the model. or accuracy, which is produced by randomness, and the Matthew correlation coefficient, which is a good performance measure for imbalanced data sets. Therefore, we decided to use this performance measure as well. Okay, but now we have talked enough about the performance measures. We will switch immediately to the results. And here we see the results for the performance of the classification model. And what we see at the first glance is that all models behave more or less have the similar performance, except the artificial neural networks. Here we have a significant higher specificity compared to the other models. However, what do we see as well? We see that sensitivity and precision are higher than the negative predicted values and specificity, which leads us to draw the conclusion that our models are generally better at classifying non-traffic relevant stops. So why could that be? It could be one explanation could be that we just have more non-traffic relevant stops in our sample. So we have more information to feed our algorithms, and maybe therefore we have better results. However, we could also assume that we could make some more subcategories, not only two, but maybe we could split the traffic relevant stops into more type of traffic relevant stops. Is it caused by accident or by congestion and so on? And maybe then we would increase the performance for non-negative predicted values and specificity. Okay, if we take a look at the informedness and the markedness, again we see some different results for the ANN, because here we have the highest informedness, so we get the most information out of our model, but the worst markedness. So it's paradoxically that it also says that we can not trust a model as much as the other different machine learning algorithms. However, random forests and XGBoost show the most balanced results. And then the last category are our overall model performance measures. And here we see at the first glance, okay, all of our machine learning algorithms work quite good and show a similar results. So we can say quite simple and intuitive machine learning algorithms, such as KNNs, are not worse compared to quite sophisticated models and black boxes such as artificial neural networks. However, if you take a look in detail and we make some groups with our top categories, we see random forests and XGBoost show the most balanced classification results and the best classification results among our arsenal of machine learning algorithms. Okay, and now 1 minute to conclude our results. What did we provide to literature is to show a 3-step trajectory data mining methodology, which includes trajectory segmentation, how is it done, the extraction of stop characteristics, and the classification of stop patterns. And we also show the selection of suitable methods for each of these steps and how these methods can be applied to a real-world dataset. And second, what I've shown you now in this part of the presentation is the evaluation of a classification algorithm, or of 6 algorithms, and we transparently show how the data balancing, the model training, and the feature attribute selection is done. But of course, there is some work in the future to do, and we provide 4 ways how we could improve our research. That would be to identify subcategories, as you have seen before. Maybe you could make more categories, not just non-traffic and traffic relevant, and this could improve the performance of the classification. Moreover, we could extend the classification task on spatially and temporally related stops from multiple trajectories, but this would need higher penetration rates of tracked vehicles, and at the moment we have no parameters for spatial and temporal vicinity, so this would be a task for the future to create these parameters or attributes. Moreover, of course, we could use more additional data sets and take them into account, for example, points of interest, bus stops, car parks, etc. For example, if you are stopped close to a petrol station, then maybe you are grabbing some thing from the petrol station. This is a non-traffic relevant stop, and this would be very interesting information for the model. However, this needs an updating process very often, because if there are new points of interest, then you need to know them, that they're valuable for our algorithms. And of course, you also could apply the method to additional problems in the transport sector, for example, accidents, accelerations, or congestions. So we have talked enough. Thank you for your attention, and now we're open to hear your questions. Thank you very much.
Wow. Well, thank you, Stefan and Carl. Excellent presentations. I really enjoy it. Now we are open the floor for questions. Marco have a question. Marco, can you speak? I see you post a message on the chat.
Yes, I can speak. Thank you. How are you? Thank you for your presentation. I'm always a little bit puzzled by applying these types of algorithms. I think I understand what you did. My question is, so you made a selection of, the best parameters to find a good solution for your data set. So now if I want to, take exactly your parameterization and apply it to a completely different data set somewhere else, what types of constraints do you foresee?
Maybe I can answer this question, Carl. Yeah, I would recommend to do the parameter training and the training of the algorithm again, because of course the data could vary in some aspects. It's not exactly the same categorization of a functional road class, for example. How do you define a high level or a low level network? So I would recommend to do the parameter tuning again. Yeah.
Okay. All right. Okay. Thank you very much.
So concerning, maybe I can also answer concerning the stop detection. So the idea was not to rely on many specific data sets, but basically the trajectory data is coming from ordinary vehicle fleets. So as you can get this data anywhere on the world. And the second data set we are using is the road network data set. In our case, it was a specific data set from Austria. But you could do the same with, for instance, OpenStreetMap data, so which has also the road classes. So also, I think that the parameterization should work also in other countries. So I don't think that you have to change a lot. So it's more or less. So what also should be the message is that the parameterization, especially, is concerned with your use case and what you want to do with the data. So as is also the case with the spatial temporal clustering. So if you want to extract other stop points than vehicle stops, then of course you have to change the parameters a lot. Yeah. But if you have vehicle data and you want to detect the stop points, I think that you can use this parameter set also with other data.
All right, all clear. Thank you.
All right. Any other comments or questions? I have a lot. If you allow me to ask some questions. So I'm just look at the one thing. I think you did a really good comprehensive estimation evaluation of your model performances, but have you thought about looking at the spatial distribution of errors to see whether there are certain locations, since your distribution of traffic relevant stops is not evenly distributed across the study area, but is that also lead to differentials in spatial distribution of errors?
So it's for me, I think, the question. So basically, since the stops, vehicle stops, can only basically occur on the road network, so you will never have a fully equally distributed distribution. So if you're using the whole space, then you always have to look at where you have the road networks and where is your data, basically. And then you could have a look at this distribution of stops, whether it is equally distributed in the within the road network. And also this will not be the case, most probably because the traffic is not equally distributed. So because you have so typically such a vehicle trajectory data is only a subset of the whole traffic, because you never have all fleets. So typically this is around 1 to 2% of the overall traffic, what you have in your data set. And of course, this follows a similar distribution than the overall traffic. So when you have more traffic on a road, then typically you also have more trajectories. And of course, if you have more trajectories, typically also more stops can occur. What could be interesting, we have not done this. So the traffic relevant stops, I would assume that they are distributed with the traffic, because also if you have more traffic, then the chance to get more traffic jams, for instance, is higher. But the non-traffic relevant stops, they are the interesting one, how they are distributed within the road networks. That could be interesting to have a closer look at this concerning this distribution. Yeah.
Mm-hmm. And yeah, I think that's a very insightful point. But what I was thinking about is more like maybe the rural area, you have a more modeling errors compared to the urban area in classified traffic stop, because maybe the rural areas have or the other way around. So to look at how the modeling error distributed in different geographical regions might get new insight about how we might need to tune the model for better performances.
Why would you assume that that different categories of roads, for instance, would have different errors?
Because, for example, in the urban area, might have more traffic accident, or may have more delivery vehicles that block the traffic, or have more left turns that people have to wait at the line. But that might not be the case in the rural area, or in the less traffic area, or in the places that have do not allow left turns, for example, one-way street.
So with the traffic relevant stops, you're fully right. I would expect this. With the non-traffic relevant stops, I'm not so sure, because there's also in rural areas there are a lot of potential cases where a vehicle could stop or the driver could decide to stop. Yeah, so for us it was rather curious how many stops occur in such data. Yeah, so if you start with your own maybe intuition and so your own behavior, then maybe you are not aware that that you stop your vehicle so often. So maybe that's also one of the interesting things, I think, if you're analyzing the stops.
Yeah. I certainly think that that could be one of the potential future studies.
Yeah. You're right.
Ali has a question in the chat. So Ali, can you talk?
Hello, do you hear me?
Yes.
I have a question. I'm a GIS student in master degree, and I want to work in this thesis, in this topic, and I want to use these algorithms in network space, like the roads and the intersections. My question is that, is this possible to use this?
Yeah, I think so. because basically you should have a network. You could take this from OpenStreetMap, for instance. And basically what we do is we are calculating, so the spatial temporal clustering algorithm works without a road network. So it's just simply clustering within a 2D space or 3D space, but we are using it in 2D space. And it simply calculates with these different spatial and temporal parameters, it calculates the stop point and says where in the trajectory where I stop and what is the stop point. And then for extracting the different attributes, which then go into the classification, there we are using the road network in order to have a look where with respect to the, or in relation to the road network, is the stop point. So is it near a main road? Is it near a lower order road? And so on. So for these attributes, you can use the road network, but you can use an arbitrary road network. So it can be OpenStreetMap or whatever you like.
Mm.
So I would say yes, it's possible to use it.
Yeah. The problem is that in this case, we can't get the data between two nodes. I mean, along the vertexes, we have no data. We can't get any data.
Okay, so you mean
like
you don't
graph
have the road segments, for instance, you don't have to have this the geometric or geographic modeling of the road segments of the roads. You only have the intersections, the intersection points.
Yeah, I mean just the intersection points and the vertexes, the roads as the vertexes.
Yeah, I think that's too less because you need the geographic, of course, the geographic data from the road network. So how the road connects the two intersections. Because otherwise, if you don't have this, you could not calculate the distance from the stop points to from the road, for instance.
Okay, thank you.
And this, as Stefan showed, this is one of the main attributes also using in the machine learning part, because typically a non-traffic relevant stop is more distant from the higher level road network than a traffic relevant stop. So this could also be maybe a part of the answer to your question, May, that also the distribution probably is not the same. So you have the traffic relevant stops are more often occurring, of course, on the higher order road network.
Yeah. So if I understand correctly, your most interest to you is the stop caused by traffic jam, right? Not necessarily traffic accident.
Yeah, because that's so. If you are using this this trajectory data, the vehicle data for calculating traffic states, then if the stop is occurring because of traffic, then you should use the delay time of the stop, basically the stop duration. You should use it for traffic information, so for calculating delays. But if this was a stop decided by the driver, so just to stop because letting out a person, then this stop duration should not be part of the traffic information. So that's the question behind basically why this is relevant or not. Yeah.
Mm-hmm. But one thing I would think quite important parameters, but that not really included in your parameter list, is the size of clusters. So how long you have a collection of stops points. Because if it's a traffic accident or traffic jam, we should see a linear pattern of stops
Yeah, we have it. Yeah, we have it. It's stop distance. It's called stop distance. We have two parameters. It's stop distance and it's the slow distance. This is also, these are two different parameters we are using. The slow distance is where the speed within the stop point is below 10 kilometers per hour. And the stop distance is the whole distance of the whole stop point cluster. So
okay. I must have missed that.
Yeah, so we are using it. Yeah.
Very good. Any other questions or comments? All right. Maybe I can have the final one if you don't mind. Is that I see you have about 392 traffic related label data, and then just about 1,600 non-traffic label data. But in most of the machine learning papers I see, they have much more label data than what you have. So do you think that if you have more labeled data, you might improve your model performances, or you think that your label data have sufficient diversity, so it's really not helping with more data?
So Stefan?
Yeah. Of course, I think more data is always better than fewer data, but I think we already have quite good results according to the performance measures. So if you take a look at accuracy or kappa, then it's already quite good. But of course, more data could probably improve our performance of classifying non-traffic related and traffic related stops. Yeah, that's also a question of resources to label the data. And that's a good point, of course. If we have, I don't know, 60,000 clustered stops, then maybe we would improve our model. Yeah, of course. Definitely.
Yeah.
So in this case, it's really hard to label the data because you have to really put in high resources. You have to look at every trajectory for itself. So where was it? How is the pattern of this trajectory? Is there maybe a nearby something rest area or something like this? So what could explain it? So it's really hard. And as you see, the traffic relevant are not occurring so often than the non-traffic relevant. So you have to label much more data. So yeah.
Well, that's kind of a counter the conventional wisdom in machine learning. Usually we think we need to have tens of thousands of label data to be able to get good model performances. But on the other hand, with small data, the machine learning model might be easier to classify the data. We really don't know when you apply to a bigger data set how the model might perform with the entire hundreds of thousands points that you have.
But actually, I think that maybe more of the same data maybe has not that impact. But more impact could have, as Stefan said, to change the learning strategy. So to not only have these two classes, but maybe to have more classes. Then again, you need more data because then you would have two less examples per class. But again, we expect that maybe if we are using more classes and more fine-grained classes, that this could contribute to a higher recognition rate.
Okay. Well, thank you very much. I really appreciate the talk and then enjoy your further explanation of your great written paper. I hope everybody also enjoy the talk as much as I do. We will have a next webinar by Dr. Maple Kwan in May. I hope you will join us in the next webinar. Thank you very much. I hope to see you in person soon in the real conference.
Thank you.
Have a good weekend.
Okay, thank you very much. Bye.
Bye.
Bye-bye.